so well. Okay, I must have changed that because it said that yesterday too. Okay. Today we're going to focus on one main topic, something called hypothesis testing, which if you had a science class before, they might have called the scientific method. That's kind of the old name that it went by. I don't like to use that name because when you call it the scientific method, it makes it sound like this is the only thing that scientists do. And that's not really true. When scientists are trying to get knowledge, they like to use hypothesis testing, but as we'll see, that's not always possible. So we're going to think about hypothesis testing. And so most of the document that this is in really describes when we look at hypothesis testing, what do we have to do? We're going to focus on this diagram, and then a lot of the description that I'll give you is actually in the notes in the document that's called hypothesis testing. Now, when we say hypothesis testing, what we want to keep in mind is think of a test that you take in a class. The purpose of a test is not to give you an A in the class. It's not to give you an F in the class. The purpose of the test is to see what you know. And in hypothesis testing, the purpose of our test is to see if our experiment is correct or not, according to what we know. So we want to keep that in mind. So let's think about the steps involved in hypothesis testing. And when we test a hypothesis, we test it in something called an experiment. So the first step is to ask a question. So think about the famous story that a lot of us heard back when we were in grade school. An English, he would have been called a naturalist at the time, not a scientist, but an English naturalist, Sir Isaac Newton, is sitting under an apple tree. An apple falls, clunks him on the head, and he wonders why the apple fell instead of going upwards or shooting out sideways. So the first thing we have to do is ask a question, or you could think of it as encounter some sort of problem that you need to solve. Now in science, the way that we get these questions or these problems is usually one of two ways. You might be sitting under an apple tree like Isaac Newton and an apple falls down and you want to find out why the apple fell down. So you might ask a question from something that you observe in nature. So that's one possibility. A second possibility is you ask a question because you do an experiment and you get some results and you want to explain those results in more depth. So for instance, if you study people who smoke cigarettes versus people who don't smoke cigarettes, people who smoke cigarettes are about 18 times more likely to get lung cancer. So what is it about smoking cigarettes that makes them more likely to get lung cancer? You might ask that question. So that would be an example of a question that comes from a previous experiment, because we had to do a study to actually find out that people who smoke are more likely to get lung cancer. Especially in modern times, probably more often than not, the way that we get our questions today is usually by looking at the results of another experiment. It's sometimes said in science that a really good experiment raises more questions than it answers. You want to find out exactly how the results occurred or why they occurred. So the first thing is we get a question and we want to find the answer to this question, or we have a problem and we want to find the solution to that problem. So the next thing we're going to do, coming down to this orange rectangle, is we're going to do some background research, which typically means reading other work that's been done in the same general field. You know, if you go out after class today and you sit down under an apple tree in your yard and an apple falls and hits you on the head, You might decide that you're going to become rich and famous by figuring out why apples fall down. I don't want to make you depressed, but I have some bad news for you. It's something called gravity, and you're probably not going to get rich and famous by figuring out that there's something called gravity. So when you do your background research, you might discover that we already know the answer to your question. Or you might discover that we don't know the answer to your question. Now, one of the things that does make science different than some other fields is in science, even if we know the answer to the question that you're asking, you can disagree with that answer and you can decide that you want to go ahead and do an experiment because you think there's a better explanation for it. You think that the answer that's been accepted is really wrong. And this is something that makes science different than a lot of fields of study. Just because something has been proposed and it's accepted, it doesn't necessarily mean that we're going to take it at face value and say that it's correct. One of the things we don't do in science that a lot of fields of study do is we don't accept the word of authority. You can be a world famous expert in your area, but just because you say this is the reason that happened, we can do an experiment and we can question whether you're correct or not. So do some background research. And actually, apples falling from trees is a good example. Sir Isaac Newton studied why apples fall from trees, and he came up with something called his law of universal gravitation. And his law of universal gravitation says every two objects in the universe attract each other. And how much they attract each other depends on their masses. Mass is kind of like weight, and how far apart they are. So he came up with an explanation. So this was 1687 when he came up with his law of universal gravitation. He did the work before that, but that was when he finally had everything in its final stages. And this was accepted as being completely correct until 1915. And in 1915, a young scientist who worked in a patent office in Europe had been studying the mathematics of gravity, and he came up with a different explanation of gravity. The scientist was a young patent officer named Albert Einstein. And the alternate explanation he came up with is something that today we call Einstein's theory of relativity. And basically, his theory of relativity shows that gravity only works for big things. Now, keep in mind, big things are anything bigger than a grain of sand, all the way up to the size of, say, a planet or a star. And it only works for things that are moving slowly, like the speed that things move on our planet. But keep in mind, things moving slowly, they could be moving 65,000 miles an hour. That's slow. Relativity shows that if things are moving really fast, or if they're really small, like atoms and molecules, the law of universal gravitation doesn't really work the way that Newton thought it did. There are other things that have an impact. So in science, you might do your background research and you might decide, the explanation that you're reading for what people are describing, that doesn't seem right to you. Now, keep in mind, if the experiment is expensive to conduct, you may have a hard time getting anybody to fund your challenge if you're challenging a well-established idea. So if we look at this yellow rectangle, now remember, this whole process is called hypothesis testing. And notice that this step is called construct a hypothesis. So you've observed something in nature, or maybe you've seen the results of an experiment that you did or somebody else did. You've done some background research and either nobody can explain what you've seen or you think the explanations are inadequate. So now what you do is you construct a hypothesis. A hypothesis is sometimes called an educated guess. A hypothesis is a possible answer to this question, a possible solution to this problem. Now notice I'm saying possible because we don't know that it's the correct answer to your question. That's why we're going to have to test this hypothesis. Now, for your hypothesis, there's a couple of things that are crucial about this when we think about, we're looking at this from a scientific perspective. You could certainly use hypothesis testing in other fields of study. But when you come up with your hypothesis, you have to be able to think of an experiment that will prove that your hypothesis is wrong. Not that it's right. You have to be able to think of an experiment that will prove that your hypothesis is wrong. So if you can't think of an experiment that will show that your hypothesis is wrong, it might be the correct explanation, but it's not a scientific explanation, because for it to be a scientific explanation, we have to have a hypothesis that you can disprove. This is one reason why science is sometimes at odds with religion. A religious explanation for something could be that, this is what God created, this is how God did things. But at least as far as I know, no matter what religion you might belong to, religions say that God is beyond human understanding. So that means that you can't do an experiment that would prove a hypothesis like this is wrong. So that could be the correct explanation for something, but it's not a scientific explanation. So that's one of the things we have to keep in mind here. We're really restricting ourselves to scientific explanations. So now we're going to test our hypothesis in an experiment. And this experiment has to be an experiment where we can imagine some kind of results that we get from doing this experiment that will show that our hypothesis is wrong. If there's no results that our experiment will give that show that our hypothesis is wrong, it's pointless to do it. Now, keep in mind, one of the problems we have in science is technological. If you go back to the early 1900s, there were some people who thought that a molecule called DNA was the genetic material. But there was a problem, and the problem was that really until about the 1940s, we didn't have the biochemical techniques to separate DNA from the rest of a living cell and to experiment on DNA. So one of the things that might make your hypothesis scientific, it's not just that it could be a religious hypothesis, we just might not have the technology to test it. So you could come up with a hypothesis today that's not very scientific. We can't do an experiment, we can't disprove it. But 100 years from now or 200 years from now, when the technology improves, we might be able to test your hypothesis. For instance, when Einstein developed his theory of relativity, there were some experiments that he proposed that there was no way to do back at that time. So we weren't sure what the results would be. But with the changes in technology that have happened, it's been about 100 years since Einstein's theory of relativity was proposed. With the changes in technology, we can now do experiments on a bunch of the ideas in his theory, and we can see if the predictions that we get from the theory are correct or not. So we're going to test our hypothesis with an experiment. Now, one of the things to keep in mind is, depending on how we word our hypothesis, we might not actually be testing our hypothesis. We might be testing a prediction from our hypothesis. Suppose I want to find out if one gender is more intelligent than the other. So if you think about that, my hypothesis might be that men are smarter than women, or it might be that women are smarter than men. Doesn't really matter for the purposes of our argument. So I have to devise an experiment to test this. Well, since I teach biology, the way I'm going to see how smart people are is I'm going to give you a biology test. So we have to have an experiment where I give you a biology test, I look at the scores, and then I divide you into the men and the women and see who got the higher scores. Well, notice that one potential, well, there are several potential problems with this, but when we do our tests, there are a couple of things. When we do our experiment, we want our experiment to give us what we call quantitative results, not qualitative results. Quantitative results are numbers. So if I give you a biology test, it has to be a biology test where you get back your score and it's a 91 or an 87 or a 65 or whatever. Qualitative results would be that I give you a biology test and you get back a score and it just says A, B, C, D, F. You know, that I'm not sure whether it's true, but there's a feeling that quantitative results are superior to qualitative results. And that if somebody else decides that they want to check your work and go back and do an experiment, that quantitative results should be easier to duplicate than qualitative results. You know, think about, you know, if instead of giving you a test, I talk to you about your knowledge of biology. And at the end, you know, I divide you into a couple of categories. Yeah, some people knew a lot about biology. Some people knew a little bit. Some people didn't know very much. Some people knew nothing. Well, part of the problem is if instead of me doing the interviews with the people, you do an interview, your idea of somebody who knows a lot about biology might be different than my idea of somebody who knows a lot about biology. Presumably, we both have the same idea about what 91% on a test does. So we think that quantitative results are a little bit easier to be duplicated. Now we have another problem with an experiment. Okay, so let's take my example. So suppose we're doing an experiment and we have our two study groups. We have men and women. We're trying to find out which group is smarter, and I'm going to give you biology tests. So, you know, if you think about my hypothesis here, my hypothesis is really that the gender of the person is what's important about the, you know, that's what's going to have the impact on your score on the exam. Is there anything else that could affect your result on an exam besides the gender? That might matter, might not, but can you think of any other factor that might affect a student's score on an exam other than their gender? Any ideas of something else that might affect a student's results?
Like if they're sick or not on a particular day, like how they feel.
Okay, yeah, you've probably all at some point in your school career had to take a test the day after you got over the flu or something like that. And, you know, usually when people either are feeling sick that day or they've been feeling sick, they don't do as well. So your health, what else? Now, keep in mind, I'm trying to measure how smart you are. That's kind of a vague term. We could also say how intelligent you are. But, you know, think about some other factors. What about your home environment that you grew up in? You might have parents that encourage you to learn and encourage you to read books, or you might have had parents that, you know, plop you in front of the Nintendo all day to play games so that you leave them alone. So your home environment could matter. So there's potentially a lot of factors that might affect the results of our experiment. And this is true if we're trying to figure out what causes people who smoke to be more likely to get cancer. For any experiment, there's typically several factors that could affect the results. So when we do an experiment, we have all these factors and we call these factors variables. So think of like a math class. Well, really the variables fall into two categories. We want all the variables to be controlled. So when we have variables that we say that they're controlled, we really want them to be as close to the same as is possible in all our groups. So if I have a group of men and a group of women, and I'm going to give them biology tests, I want to make sure that their health is the same. I want to make sure that their age is the same. You know, if all the men are 95 and the women are 25, the men might be more senile. I want to make sure that they have the same socioeconomic background. So there's all these other factors that I want to be equal in our two groups. Because imagine that I test a group of women and the women are 25, I test a group of men and the men on average are 95. Well, if the two groups don't score the same on the exams I give them, how do I know whether it's the gender that's causing that or whether it's the age factor that's causing that? So all the factors, all the variables that could affect our results, but the ones that we don't want to affect our results, we need to be as close to equal as possible in all our different groups. We'd like to have our groups of men and women be the same age, the same health condition. They went to the same grade school and high school if possible. They, you know, everything is the same except their gender. Because then if we get some differences, assuming we've actually accounted for all the other factors that could affect the results, then we can be sure that gender was what caused the results. Now, this is one of the reasons why it's very difficult to do experiments on people. If I'm doing a study of nutrition and I'm looking at lab rats, I can keep a bunch of lab rats in the same small aquariums in my lab, so they're all in the same type of environment. I can feed them exactly the same food every day. I can give them the same amount of water. I can let them run on their little exercise wheel the same amount of time. If I have a group of people that I'm testing, I can't control people that closely. First of all, people wouldn't let me, but secondly, the government wouldn't let me do an experiment like that, where I controlled your lives that completely. So it's very difficult to do experiments with people. So we'll talk about that a little bit later on. So our experiment needs to give us quantitative results, and we need to control all the variables we're interested in except the one that we think causes whatever we're talking about. So gender in my example. Now, notice the other thing we have to worry about is just whether our procedure works. If I was just giving you a test, that would not be that complicated. You know, we need a desk and a piece of paper and a pencil to mark your answers with. But when I was a student, for instance, I was studying how much oxygen some insects breathed in. And to do this, I actually had to come up with a small chamber that I could put the insects in. And it had some tubes running into the chamber and running out. And I had to be able to make the chamber airtight and then measure how much oxygen that was in the air that flowed into the chamber and how much oxygen that was in the air that flowed out of the chamber. So I could see how much the insect actually breathed. And I had to make sure that the chamber was sterile, so there weren't bacteria in there using any oxygen. So if you have some sort of special equipment, you have to find out if that's working the way you think it is. So if your procedure isn't working, you have to go back and fix things and start over again. I actually had to build about 3 or 4 different types of chambers for my insects because it was hard to get one that they would cooperate with. And sometimes you need help. I had a friend who ended up building little, you'll probably laugh at this, little treadmills that the insects ran on. So we could measure how much oxygen they used when they were exercising compared to when they were just sitting still. Now, if your procedure is working, then you collect all the data, all the numbers, and you're going to analyze this data and draw your conclusions. Now, when you analyze the data, there are 3 different possibilities. One possibility is this second purple over here. The results that you get either don't align with the hypothesis at all, or they only align a little bit. If they don't align with the hypothesis, we say that we reject the hypothesis. It isn't correct. It doesn't explain what happens. Suppose my hypothesis is men are smarter than women. I give you biology tests, and on average, the women score higher on every test throughout the semester. That doesn't really go along with my hypothesis. My hypothesis was that men are smarter than women. So if that's the case, we reject our hypothesis. Now, notice sometimes instead of rejecting the hypothesis, we might just decide to modify the hypothesis. Think about what my original hypothesis was. Men are smarter than women. Well, one possibility is, I said I was going to test this doing an experiment. I was going to give you biology tests. But one problem with that idea, now, of course, I study biology and I teach biology, so I think biology is important, but is giving you a biology test really a very accurate way to measure overall how smart you are? Different people have talents in different areas. I have a friend who can play like 10 different musical instruments. She can pretty much pick up a musical instrument and start playing it if you give her a day to practice. And I can pretty much play a musical instrument if you give me about a year to learn how to play it and practice. And then I might be able to play, Mary Had a Little Lamb on my kazoo. So maybe using a biology test to measure how smart somebody is not very accurate. So if our hypothesis is men are smarter than women, notice that if our experiment just involves giving you a biology test, that's not really a measure of how smart people are. What we're really measuring is a prediction from the hypothesis. Because if men are smarter than women, then logically, they should score better on biology tests. But maybe we need a broader measure of intelligence than just giving you a biology test. Maybe we should give you tests from a bunch of different school subjects. Or maybe we should give you something called an IQ test, which supposedly just measures intelligence. Although all the IQ tests that have been studied very carefully have some cultural bias in them. Because, if I design an IQ test, I know I'm smart, so I'm going to design the IQ test so that people who know the same things I know score well. If you design an IQ test, most people think they're smart. So guess what? If you design the IQ test, you're going to design the IQ test so that people who know the same things that you do score well on your test. The problem is this is culturally biased, but we haven't really figured out a way to eliminate that cultural bias from designing something that's supposed to be non-biased, because every human comes with some biases. Now, another possibility is when we do the experiment, the results agree with our hypothesis. My hypothesis, or my prediction from my hypothesis, was that men will score better on the biology test. And every guy in the class scores better than every woman in the class on every test all semester. So my hypothesis seems to be correct. But notice one of the things that makes science different from some other fields is in science, if the results agree with your hypothesis, we don't say that the hypothesis is correct. If the results disagree, we say that we reject the hypothesis. But if the results agree with the hypothesis, we just say that we don't reject the hypothesis. This experiment didn't show it was wrong, but the next experiment might show that it's wrong. So technically in science, we never really say that our hypothesis is correct. Now, for some hypotheses, they've been tested dozens or hundreds or thousands of times, and we haven't been able to reject them. Well, if we do a dozen different experiments and all the experiments agree with our hypothesis, after a while, we get to be pretty certain our hypothesis is correct. But still in science, technically, we never say that our hypothesis is correct. We just say that it's not rejected for now, for the time being. And some people don't like that about science because they want something more definite. I've heard some people say, well, is coffee good for you or not? 2 years ago, they said it was great. Now they're saying not so good. Why? Because in the intervening 2 years, somebody's done some experiments and has shown that coffee has some negative effects, perhaps. So we kind of revise what we believe depending on what the data tell us, what the experiments reveal. Now, the final step in this process is we have to communicate our results. And really not just the results, but we communicate this whole process, beginning back with when we asked our question, how we did our background research, what we found out when we did the background research, what's our hypothesis, how did we set up our experiment, how did we control the variables that we didn't want to affect our results, what were our data, what numbers did we actually get. So we have to tell all of this. And we can't just communicate our results to anybody. We have to communicate our results to people who are specialists in this field of study. Imagine that you come up with a new drug that you think will prevent heart attacks. You have to present this information, this whole process where you tested this drug in an experiment. You have to present this to other people who work on pharmacological treatments for heart disease. Why? Well, if you present them to a bunch of people like me who studied reproduction in insects, I'm not the best person to really judge whether you conducted your experiment correctly, whether you controlled all the variables that should have been controlled. So you have to communicate your results to other people who are experts. And this is something called peer review. P-E-E-R, peer, these are your equals. These are people who are experts in the same field. And this is one of the things that is kind of falling apart in science right now. Because with the internet, really, you don't even have to conduct an experiment. But even if you conduct an experiment, you don't necessarily have to let other people who are experts judge if you conducted that experiment correctly. You can just go online and you can say, look, I fed one of my little brothers broccoli. I didn't give the other one broccoli. The one who ate all the broccoli was much healthier. So broccoli is good for you. That's not really a scientific test of whether broccoli has any health benefits. That's what's sometimes called anecdotal evidence. You hear anecdotal evidence from people a lot of times. This is, what President Trump used to say when he was in office, when he would talk about different treatments for the coronavirus. He would basically say, well, I know a person who had this and they got better, so it must be better for you. No, that doesn't necessarily mean anything. If you give a bunch of people the same medication, some of the people will get better, even if the medication has nothing to do with it. So this is why we have to have a scientific experiment. Now notice we said that you might decide to modify your hypothesis. If you modify your hypothesis, it's a little bit different. So then you have to test your modified hypothesis in an experiment and do the things that we talked about. Make sure that you get quantitative results. Make sure that you control for other variables that could affect your results. So you don't just get to modify your hypothesis and say, well, now it's correct. You have to go through the whole process of running the experiment, analyzing the data, and figuring out what the data means. Now, basically, these are things that we should do with any type of information that we're trying to establish scientifically. As I say, one of the downsides now with the internet, but also with, as I'm sure you're all aware, there's a 24/7 news cycle. And so one of the things is, in science, it's always important to be the first one who, discovers something. Person who's second doesn't get much credit. You know, we know that Christopher Columbus was the first European in North America after the Vikings anyway, but I sure don't know who was second after Columbus. So there's a rush on scientists' part too, to speed things up. And unfortunately, it results in some sloppy conclusions. There were some experiments done on using a drug to treat breast cancer in women, and the drug seemed to work. It was approved, and it was actually used for about 10 years before it was discovered that somebody finally decided to do the experiment and see if they could duplicate the results. Was discovered that the original researchers had falsified all their data. The drug that thousands of women had used to get their treatment for breast cancer didn't do anything. You know, so this is one of the problems that we have in science. When we let things kind of slip through the net, this might seem like a lot of steps to go through. But if we don't go through these steps, we don't necessarily know if we have an effective treatment for a disease, or if we just have some basic knowledge about how nature works. Now, not always, but sometimes after we do an experiment and the results align with our hypothesis, so remember what we said, that means we don't reject our hypothesis. So sometimes when the results align with our hypothesis, we test the experiment again in a slightly different way. And some hypotheses in history have been tested hundreds or thousands of times. So for instance, earlier we mentioned something called Newton's law of universal gravitation. And his law of universal gravitation was tested in hundreds of different experiments. Now, they couldn't test it with molecules, they couldn't test it with black holes, which is why they couldn't show that it didn't apply to everything. But Newton's law of universal gravitation seemed to always work. That's when it really became a law. In science, a law is something that started out as a hypothesis. It's been tested in lots of experiments, and we've never been able to reject that hypothesis. So hundreds, maybe thousands of times that hypothesis has been tested. And if it's never rejected, if the results always agree with what the hypothesis predicts, then after a while, we sometimes start to call it a law. Now notice, a law is a good example of something that we see in science that gives scientists problems. A law in science has a different meaning than a law does in everyday language. And a lot of terms that we use in science have a different meaning than they do in everyday language. But it almost always causes problems when scientists use the word one way and non-scientists, everyday citizens, use the word a different way. Think about the word law. In everyday language, a law is something that's established by maybe the town you live in or the state or the country. But man-made laws can be broken. There's a speed limit on the street out by my house. You can go faster than the speed limit if you want. You might get stopped and have to pay a fine, but you can go faster than the speed limit. There's nothing that's stopping you from going faster than the speed limit. On the other hand, if we look at laws that we develop in science, if we look at Newton's law of universal gravitation, at the college, my office is on the 4th floor. You can't open my window and crawl out and say, I'm going to disobey the law of gravitation. I'm not going to go down when I crawl out the window. I'm just going to float on the air. If you try that approach, I suspect you'll get carted off in an ambulance. So man-made laws, you can break. Natural laws, you can't break. Why? Because natural laws describe how nature works. So this means that if the law is correct anyway, which if we've tested it in thousands of different experiments, we're pretty certain it is. If the law is correct, you can't disobey it. You can't break that law because it describes what happens. Now, if we put a jetpack on you, you might not fall down when you crawl out the window, but that jetpack is actually providing some energy that keeps you from falling down. There's another word that's very similar to law. Now, Newton's law of universal gravitation really only describes one thing: how two objects attract each other, what their gravitational pull is on each other. Now, that does describe a lot of things, like why the moon rotates around the Earth. But sometimes we have a basic hypothesis that we start with, and it describes a much wider variety of activities. So when we test a hypothesis hundreds, thousands of times, and we don't reject it, but it really only describes a very narrow slice of nature, we call this a law. If we have a hypothesis and we test it hundreds or thousands of times and we don't reject it, but it describes a much broader part of nature, we call it a theory. So again, there's a problem with the word theory. Remember back at the beginning of our discussion, we said when you construct a hypothesis is a possible explanation for what happens. It's not necessarily the correct one, depends on the results of all our experiments. But a theory is something that is a hypothesis. It's been tested in hundreds, thousands of experiments. We've never rejected it. And since we've never rejected it, we're almost positive it's correct. So when we talk about Einstein's theory of relativity, sometimes people who aren't scientists say, well, even scientists admit it might not be right because it's just a theory. So that's something they're not sure about. And that's because in everyday language, when people who aren't scientists use the word theory, they really mean the same thing as scientists do by the word hypothesis. A hypothesis is a possible answer to a question. And in everyday language, that's what people mean by the word theory. The example I always give is I have a friend and I feel sorry for him. He's a Cubs fan instead of a White Sox fan. So he always has a theory about why the Cubs aren't in the World Series this year. Well, it's not really a scientific theory. To have a scientific theory about why the Cubs aren't in the World Series, you'd have to have a time machine. And you'd have to replay the Cubs season several different ways with different players getting injured, with different pitchers pitching more innings. Then you could call it a theory in the scientific sense. But what my friend really has, his explanation for why the Cubs aren't in the World Series, it's really what a scientist would call a hypothesis. It's a possible explanation for why the Cubs aren't in the World Series. So we're going to see several other words like this throughout the semester. So we have to keep in mind the scientific definition of a law and the scientific definition of a theory. And unfortunately, even a lot of scientists don't necessarily, they're not real careful when they use these words. So they sometimes use law or theory in the non-scientific meaning of the word. But this does make it difficult for people who are scientists and people who aren't scientists to communicate. Because if a scientist calls something a law, you can't break it. If he calls something a theory, he's almost certain it's correct. So we want to keep that in mind. So hypothesis testing is how we would like to get our information in science. But there are several problems with hypothesis testing. Remember, I mentioned one earlier. I can't really do experiments on people. for a lot of animals, I can do experiments, but it's really not accepted to do experiments on people. So this is one potential problem. Another potential problem is some experiments are just beyond our capabilities. If we look at certain experiments or certain hypotheses, I should say, in astronomy, we can't really test them in an experiment because we'd have to rearrange planets and do things like that. And we don't really have the ability to rearrange planets. So we're kind of stuck with what we have. So there can be several reasons why we can't test something in a hypothesis testing experiment. So how else can scientists get their knowledge? And I'm skipping over some of the steps, but when we can't do experiments, one of the things that scientists do is scientists build models. And there are two different types of models. There are physical models. So you could think of if you ever assembled toy cars or airplanes or, some of the Star Wars fighters or something like that when you were a kid. One student that I worked in graduate school with built large models of dinosaurs. Not life-size, but 3 or 4 feet high, foot or two across. And he built them out of materials that are similar to bone and muscle and skin. And then he puts them in wind tunnels and he puts them in chambers with different temperatures to try to see if dinosaurs could have been warm-blooded. And the basic explanation that we're pretty certain about now is that some dinosaurs probably were warm-blooded. So they might not have been cold-blooded like we think. But most of the models that scientists use are actually mathematical models. And they just involve very complicated sets of equations that are programmed into computers, because computers can do the calculations so much faster and so much more accurately than people do. And a good example of this is, think about during the pandemic when you used to see pretty regularly all these predictions about what the death toll would be in another month or another 2 months. And sometimes there was more than one prediction. Why? Because they were using different models. Later in the summer, we'll see the same thing when hurricane season starts. If you've ever seen any of the weather predictions about where a hurricane's going to go, they usually show where the hurricane is now, and then they show you a bunch of lines. Some are further east, some are further west, some are kind of straight up. Why do they show you all these? All these projections, all these predictions are based on different models. The European Union has one. NOAA, the National Organization for Atmospheric something or other, has one. NASA has one. And depending on exactly what factors they take into account in their mathematical equations, they don't get the same results. So now the nice thing about mathematical models is, if you predict where hurricanes are going to go and all your predictions are off, you can go back in and you can kind of change some of the values in your equation that you're using. And you can kind of tweak it to make the predictions better in the future. So a lot of things that we study now are studied using models. Now, I mentioned that usually we can't do experiments on people because of ethical reasons, and people aren't very cooperative. So what do? We do a survey. Since I can't control your diet, one way I could find out, if certain types of foods lead to better health is I could give you a survey and I could ask, how often do you eat fruit? How often do you eat broccoli? How much chocolate do you eat a week? How much alcohol do you drink a week? How often do you exercise? And then I could ask you some questions about your health. Have you ever been diagnosed with cancer? Do you have heart disease? I could ask you some questions. And if I do this with thousands of people, I may be able to come up with some connections. Hey, people who run marathons are hardly ever overweight and have heart disease. So we can do a survey and we may be able to draw some conclusions. But there's one huge disadvantage to doing surveys to get scientific knowledge. They actually did a study once and they checked people who were participating in a health survey, and they had the people fill out their surveys. They had to do it several times. It took place over a period of 2 or 3 years. But guess what they found out? People lied on the surveys. When they went into their doctor, nobody told the doctor they were sitting on the couch binge watching whatever their favorite show was. Nobody told their doctor they were gorging on hot fudge sundaes. They told the doctor that, they only ate fruits and vegetables, that they exercised every day. So we have to keep in mind that doing surveys may or may not be reliable. Most of the health surveys that have proven useful have actually involved doctors and nurses working at hospitals. And some of these health surveys have been going on for 30 or 40 years. So assuming that the doctors and nurses are being honest, which is a big assumption, but assuming that they're being honest, then what we see is that we can draw some definite conclusions from what we've learned from this study, the Framingham study. Particularly, it's focused on heart disease. So keep in mind, hypothesis testing is our first choice. If we can use hypothesis testing to get information, to learn something scientifically, this is what we want to do. If we can't use hypothesis testing, then our other choices are we can make a model, either some sort of physical model or a mathematical model. And if you think about predicting hurricanes, obviously you can't experiment. We really couldn't make a hurricane if we wanted to today. We have a hard enough time just predicting where the hurricane's going to go when it forms. So we can use models, we can use surveys, but really hypothesis testing is the key step that makes science science. Some other fields use hypothesis testing occasionally, but in science, this is the main way that we gain our knowledge. So are there any questions about hypothesis testing and other scientific ways to get knowledge before we leave this topic?
No.
Okay, if there aren't, I'm going to stop screen sharing for now. So notice in today, if you think about it, what we focused on is what makes a field of study a science field. Because besides science, we have the social studies areas, we have what are sometimes called arts and humanities. So there are different branches of knowledge. So science isn't the only way to get knowledge, but it covers some things that we consider to be important. The other thing we have to keep in mind is that when we think about science, we want to stay away, as I mentioned before, from the idea that these other ways of getting knowledge are somehow inferior to science. It partly depends on what we're trying to study, what the best way to study that subject is. So now that we have more of a feel for what makes something a science, the next thing we want to focus on is what makes science a biology. Instead of, geology is a science, physics is a science, chemistry is a science, astronomy is a science, lots of different sciences. So if I asked you, what is biology? Could you tell me what biology was? Could anybody give me a basic definition of biology?
The study of life.
Study of life, okay. And keep in mind that logi on the end always means study of, and bio means life. We're going to see bio in a lot of words we see this semester. Now, here's the problem. And I'm not going to pick on Michelle just because she gave me that answer, but what is life? If I gave you something, I'm guessing you could tell me whether it was alive or not. There's a few things that are kind of iffy, but you could probably tell me something that's alive. But, what's the definition of life? That's a little bit harder.
Mm.
And the reason I don't want to pick on anybody is because, you know what? As scientists, we don't have a very good just definition for life.
Mm.
Instead, when we think about life, we think about certain characteristics that living things have, certain things that living things can do. And, we're going to be taking kind of a technical approach to life this semester. So one of the things that has driven me crazy for the past year and a half, while we've been in this pandemic situation, Lysol has some commercials on different shows that you watch, and they tell you that Lysol kills 99% of the coronavirus. Well, I've got a problem with this because guess what? Viruses are not alive. So how do you kill something that isn't alive? That would be like seeing a commercial for the hardware store where they sell axes saying that we can kill 99% of your desks. Okay, what does that mean? So when we think about living things, we're going to focus on what characteristics do living things have. So we're not going to have a precise definition. We're going to have a definition that says, if you can do A, B, C, D, E, F, G, you can do these things, you're alive. If you can't, you're not. And it turns out viruses can't. Viruses can only do two things that we associate with living organisms. Viruses can reproduce. Now, they're a little bit weird though. Compared to other living organisms, viruses have to be inside a living cell to reproduce. A virus can only reproduce when it's inside your cell or whatever type of thing it infects. All viruses don't infect people. There are viruses that even infect bacteria. So viruses can reproduce. And when a virus reproduces, it can evolve. And living things can evolve. That's one of the characteristics of living things. But living organisms also use energy. Viruses don't use energy. Living organisms have a very complicated chemistry. The chemistry in viruses is much simpler. Living organisms are made of some small units called cells. Viruses are not made of cells. And besides viruses, it turns out there are other things. You might have heard of a disease called mad cow disease. Mad cow disease is caused by something even smaller and simpler than a virus. So again, it's something that's not really alive the way that we technically define life. So we're going to stop here for today. Tomorrow we're going to focus on what is it that makes something biology. And tomorrow we'll probably be in class the whole time. Don't forget, before class tomorrow, turn in the note card. So you should be able to find that under the content for week 1. And you should also be able to find that under the assignments tab. Anytime we have an assignment, it should be in both of those locations. And it should have the number of points that it's worth. This assignment is worth 5 points. And notice that at the end of the semester, we're going to have more than 1,000 points. So this is kind of a minor portion of our assignments. Remember what I said. This is really just to kind of get you used to how we're going to turn things in. And we'll have another very short assignment tomorrow that'll be due, in a couple days after tomorrow. And then most likely we'll have our big test, our test on chapter 1 on Monday. So any questions before we leave for today? If not, I will let you go. So enjoy the rest of the day. Like I say, tomorrow we'll probably be here the whole day, so pretty close to noon before we break up.